Okay, gang, what I want to do in this next example is, well, first of all, take a little break from the derivative rules. Again, we've got one more left, okay, of the differentiation rules. Found how to take the derivatives of the trigonometric functions. We know how to take the derivative of polynomials and so on and so forth, okay? In this particular example, I want to just try something different, okay? I want to rely on all of the work, most of the work that we've done up until this point, okay? Here's a function. This function, I'll write it up here. This graph is the graph of this function. Y equals the natural logarithm of the absolute value of x. Okay, now note that the domain of this function is all real numbers except 0, right? Because you can't take the logarithm of a negative number, and you can't take the logarithm of 0. But we have absolute value bars around the argument, so we don't have to worry about logarithms of negative numbers. Only 0 do we have to worry about. And here's what its graph looks like. Okay, what I want to do is I want to try to guess at the derivative of this function. Okay, and I don't want to use the limit definition of the derivative. I don't want to do anything like that. Okay, I just want to rely on previous work. All right, so let's see. Here's some analysis that we can do purely based on work we've done before. Let's do this. Notice at the x-intercept, 1, 0, I could put a tangent line. Okay, and based on the grid around it, I can estimate, actually, it's not even an estimate. I think I can get it exactly, huh? It looks to me like the derivative, whatever it is, I'm going to call it f prime, at x is equal to 1. Let's see, the rise would be what? 1 unit over 1 unit. So it looks like the slope there of that tangent line is equal to 1. By symmetry, or by the grid, if I put a tangent line right here at the other x-intercept, okay, it looks to me like the derivative evaluated at x equals -1 must have a slope of -1. Okay, now I don't know what the derivative of this function is, gang. I don't know what it is, but I'll tell you what, I've got 2 points on its graph already. How about that? Bet you didn't see that coming, huh? All right, what else can we say? Well, how about this? Suppose I was to go on and put more tangent lines all over the graph of the function. Let's start to the right of 0. Okay, let's start to the right. All right, so here's some tangent lines out here. I'll use green. Okay, so here's all these, you can get an infinite amount of tangent lines on there. Okay, what do you notice about them, gang? What do you notice? Well, how about this? Do you notice that as we take the limit of whatever the derivative is, and I don't know what it is, okay, but I can say this, as I approach the origin from the right-hand side, those tangent lines are getting steeper, okay? They're all positive slopes, and they're getting bigger and bigger. So I'm going to say that the limit of the slope function, whatever it is, the derivative, as x approaches 0 from the right-hand side, it's going to increase without bound, okay? On the other hand, as I go out in the other direction, now we haven't talked about that kind of a limit yet, but I'm going to appeal to your sense of intuition, because much of calculus is plausible intuitive, okay? And ask you what happens to the slopes as we go all the way out to the right. Keep going forever, all the way out to the right. Yeah, they're getting less steep, right? They're getting shallower, all right? In fact, here's how we write going all the way, values of x going all the way to the right forever means x goes out to positive infinity. Okay, we haven't discussed that before, so that's kind of new, but intuitively, I think it would make sense that the slopes, okay, remember that's what the derivative represents, the slopes of all tangent lines are getting more and more horizontal, so therefore going to 0. Okay, now you can use the symmetry of the graph, gang, right? Put some tangent lines on this side, all over the place on this side, put some tangent lines. Okay, and I think we can argue rather convincingly that as we approach 0 from the left-hand side, what can we say about all the slopes of the tangent lines? Okay, now mind you, you're coming in this direction now. And the closer you get to the arc, look, they're getting steeper and steeper, but in a negative sense. Okay, and again, if we were to go all the way out to the left forever, the tangent lines are getting more and more horizontal. And we would write under here, x goes to negative infinity. And we'd have something like this. Okay? Now remember from my work earlier, we said that anytime you take the limit of a function and you get back either positive infinity or negative infinity, then that means that the number you're approaching is a vertical asymptote. So that tells me, again, this one right here, this here, and where is it? This one here. Okay, these two limits tell me that x, the line x equals 0, which is the y-axis, by the way, is a vertical asymptote for the graph of the slope function. Now, what do you think that looks like? Can you, let me ask you this, and can you make a graph based on that information? I'll bet you could. I love those kind of problems, right? Where they give you the stuff and you got to come up with a graph. Well, let's see what we can come up with. All right, I've got another piece of graph paper here. All right, so here is our y-axis. Okay, now, according to this, the derivative at x is equal to 1. Let's go 1, 2, 3, 1, 2, and so on. Okay, now according to the first one, the value of the derivative at 1 equals 1. So that gives me a point right here. Okay, takes care of this. The next one says the value of the derivative or the y-coordinate at x equals -1 is also -1. So that gives me this point right here. Okay, what do you think? So far, so good? That takes care of this condition. Okay, so whatever the graph of our derivative looks like, gang, it has to go through those two dots. Now, this one says that on its way through this dot, as we approach the origin from the right-hand side, the graph has to increase with that bound. Remember, we said the y-axis, or the line x equals 0, is a vertical asymptote. So that suggests this. Takes care of that. This one says that as you go all the way out to the right-hand side instead, okay, as the graph passes through that dot, it has to decrease to a value of 0. Okay, so the limiting value is 0. So that suggests the graph is going to look like this. And that takes care of this one. Okay, there's no new math here, gang. No new math, except maybe this infinity limit as x goes to infinity, negative infinity, but we're appealing to our sense of intuition. All right, this one says, all right, this limit says, okay, as the graph passes through this dot and gets closer to 0 from the left, the graph has to decrease without bound. So that means like this. That takes care of this one. This one says, as the graph passes through this dot and continues all the way out to the left forever, it has to approach a limiting value of 0. That suggests this. Okay. Now, hopefully you recognize that graph from your pre-calculus days. Do you know what that graph is? We're calling it the derivative function, to be sure. But you should recognize that, gang. You know what that is? Yeah, it's the reciprocal function. That's right. That's right. Okay, so what we're saying geometrically now, okay, is that the derivative function for the logarithm of the absolute value of x, whose graph is this blue curve here, what we're saying is that its derivative is 1 over x, otherwise known as the reciprocal function, okay? Now that's not proof, right? We didn't prove anything. If we were going to actually prove this, we would use one of the limit definitions of the derivative, you know, f of x plus h minus f of x, all that stuff. But I think you could agree, we made a rather compelling geometric argument, okay? Remember, calculus, much of it is plausible and intuitive. And I don't think anybody doubts their eyes here. All right, so I'm going to say this then, okay? For y equals the logarithm of the absolute value of x, whose domain, by the way, is all real numbers except 0, we just found that its derivative function, right? Notice I'm using the operator notation for no particular reason, just because I like it. Okay, so the derivative of the logarithm of the absolute value of x is equal to the reciprocal function 1 over x. Okay, the reciprocal function, which is 1 over x. Isn't that interesting? And that's good to remember, gang, because that kind of comes up pretty often. Okay, so the derivative of the logarithm of the absolute value of x is the reciprocal of x. Okay, here's another example. All right, here's another example where we rely on work that we've done already. Okay, let's suppose that I want to define the derivative of the natural exponential function e, okay, or e to the x, right? The natural exponential function e to the x. Now you remember this from your pre-calculus days, right? Exponential growth and decay models. You remember PERT, right? That was continuously compounded interest, right? That kind of stuff. All right, so the domain, by the way, for e to the x is all real numbers. I want to calculate its derivative, but instead of using a graph, I'm going to use the limit definition of the derivative. Here's what that looks like. Okay, so f of x plus h minus f of x. Now I know by a property of exponents, and there are many to use to be sure, right? I can rewrite the first term as e to the x times e to the h. Okay, and then gang, I'm going to factor the e to the x out of those two terms. And I'm going to put it over here. Okay, so that leaves me with just this. It doesn't leave me with just this. What I'm getting at here, and the reason that I did this, is because, gang, in that expression, notice that the only thing that's changing in the whole thing is not the letter x, it's the letter h. Okay, in that whole expression, the only thing that's changing is the letter h, not the letter x. Okay, now if I was to attempt direct substitution at this point right here, I would have had 0 in the denominator, which is no good. But in the numerator, look, e to the 0 would have been 1, in which case I would have had e to the x minus e to the x, and that would have led to the indeterminate form 0 over 0, which means further investigation is necessary. That's what I'm doing here. This is my further investigation. What I want to focus on is this part right here, because it is that stuff in the blue parentheses that's actually changing because the h is changing. All right, now, one of the first ways we evaluated limits was by examining tables. Okay, now this is a two-sided limit. So what I did was I made a table of values. I made two tables, one where h was approaching 0 and from the left-hand side, and one where h was approaching 0 from the right-hand side of just the expression in the parentheses. And look what I found, gang. Here's the table. Look what I found. Okay, notice as h approaches 0, look at this, from the right-hand side. Okay, in this case, h is approaching 0 from the right-hand side. What can you say about these values as you go down the table? Yeah, what are they approaching? Good, they're approaching 1. All right, now look at the other table. This time I'm approaching 0. H is approaching 0, but from the left-hand side. What can we say about the values in the table this time? Good. Those are approaching 1 as well. So therefore, the two-sided limit, okay, go back to this expression right here. The two-sided limit of that expression in the parentheses is equal to 1 times the e to the x that was there already. Okay, look at that. Isn't that interesting? So what we found, gang, is that the derivative of e to the x is itself. Okay, it's the only function that does it. The derivative of e to the x is itself. Very interesting, isn't it? And pretty cool too. Okay, here's an example. If I wanted to find the derivative, right, of 5e to the x, well, the constant multiple rule says I can set the 5 aside, but otherwise, the derivative of e to the x is just itself. Okay? The derivative, what about the derivative of e to the 2x? Yeah, now, you know, I know that the derivative of e to the x, e to the 1x is itself. But what about e to the 2x? Well, maybe what I'll do is I'll use a property of exponents. E to the 2x is the same as e to the x times e to the x. And then I'll do the product rule. Okay, let's use a different color for derivatives. Product rule says the derivative of the first factor times the second factor. The derivative of the first factor is itself, okay, times the second factor plus the derivative of the second factor, here's the second factor right here, times the first. And the derivative of the second factor is itself. All right, now simplify. How about that? Okay, so the derivative of e to the 2x by the product rule is 2 times e to the 2x. What about the derivative of e to the 3x? I'll bet you know where this is going, don't you? Right? Let's write the derivative of e to the 3x as e to the x times e to the 2x by the property of exponents, and then apply the product rule again. Okay? All right, let's see. Product rule says the derivative of the first factor times the second. Well, the derivative of the first factor is itself. Plus, then we take the derivative of the second factor, which is e to the 2x, and we just found that in the previous example, right? The derivative of e to the 2x, right here, 2 times e to the 2x. Simplify. Okay? Can you tell me what the derivative of e to the 4x is? Very good, gang. Very good. Okay. And maybe why don't we just say this? Because we could be fooling around like this all day. Why don't we just say this one time for all time, shall we? Why don't we just say that the derivative of e to the kx, where k is some real number, is equal to k times e to the kx? Why don't we? Okay. All right. Now, before we close this out, I think it's worth mentioning what we've got so far. Okay. We now know over the course of the last, or all the work that we've done, right? We know that the derivative of the basic absolute value function is the absolute value of x over x. It was the very first derivative we ever found. We know that the derivative of the basic reciprocal function is negative 1 over x squared. We know that the derivative of the basic square root function is 1 over 2 square root of x. Okay. We know that the derivative of the logarithm, natural logarithm of the absolute value of x, is the reciprocal function. don't we? Yeah, we do. We know that the derivative of e to the x is itself. And also that the derivative of e to the kx is k times e to the kx. And we know all of that, don't we? We know that. How about this? We know that the derivative of the power function x is equal to 1. We know that the derivative of the basic squaring function, what's the derivative of x squared? It's 2x. What's the derivative of the basic cubing function? By the power rule, it's 3x squared. What do you think of that? Let's see, is anything missing? Do you recognize that list of functions, everybody? Absolute value of x, the reciprocal functions, square root function, the logarithmic function, the exponential function. We got the power functions, the identity, the squaring, the cubing. Oh, the constant functions. We know that the derivative of all constants are equal to zeros. Oh my goodness, look at that guy. We have at our disposal the derivative of the 9 basic functions from pre-calculus. Isn't that something? Wow, the places we're going with this stuff, huh? How about that? Next thing we're going to figure out is what to do with all of these when they come as compositions.